My topic is enhancing ensemble learning and transfer learning in multimodal data analysis by adaptive dimensionality reduction. First, we'll go through the abstract of this topic. Traditional ensemble and transfer learning techniques doesn't give good results on multimodal data, which is contrast. It is because let us consider in general cases, ensemble learning and transfer learning techniques gives good results. Like because ensemble learning considers like more models instead of single model, generally gives good results comparatively remaining. Why this happens? Traditional ensemble learning and transfer learning methods assume that data used to train and test models is of similar quality, and it assumes that it has a balanced distribution. It also assumes that all the features are equally reliable. But however, in real cases, multimodal data sets where data comes from different sources like sensors, images, and signals, it will not apply. Example, some data sources may be noisier or kind of less accurate than the others. The amount of data can vary across sources, and so we have these many negatives. This paper processes a method to improve data analysis on multimodal datasets by addressing the challenges of inconsistent data quality, sparsity, and class imbalance. This will try to cover these all. This paper will propose a method to cover all these things. The authors propose a graph-based adaptive dimension. Like basically, we will be doing a graph-based adaptive dimensionality reduction method that identifies the most important features in different data sets, subsets. Let's go through the background and motivation summary. What's ensemble learning? First, let's discuss the basic terminology used, like ensemble learning, transfer learning, and so on. Types of ensemble learning and types of transfer learning. What's ensemble learning? Uses multiple models to improve data analysis. It considers more models instead of training on a single model. It will consider many models, like a stacked model. There are two types of ensemble learning: model level and data level. In model level, ensemble learning combines predictions from different models. That means it uses more models. Data level means splits data into diverse parts to enhance learning. Uh, if it is useful because if the data is having so many distributions, like local distributions, the model can learn from all the local distributions, something like that. And we'll talk about transfer learning. It is useful when training and testing data come from different distributions. Like the task is same, but the data used is the task is for example, image identification. It is trained on some other distribution. For example, some animals or something like that. If we wanted to train one more, if we want to take that one for use that model to fine tune on person's image, and that is transfer learning. We generally focus on transdictive transfer learning, which transfers knowledge from labeled to unlabeled data in a related domain. Like domain is same. Dimensionality reduction commonly used in both ensemble and transfer learning to improve performance and reduce complexity. Our main motivation is traditional methods struggle with multimodal datasets. This work proposes an adaptive graph-based dimensionality reduction method to enhance ensemble and transfer learning in such context. Main approaches in Let us see the main approaches in model level ensemble learning. There are three approaches: bagging, boosting, and pruning. In bagging is we'll take a bootstrap sampling. Multiple subset of training data are created by sampling with replacement. It's randomly taken, and some weak classifiers are trained. Like what weak classifiers are the simple models that are trained on these subsets. When combined, then it will be combined by majority voting. Like majority prediction will be will be given the final prediction. Limitation: sensitive to training data and may not work well with the noisy datasets. And we'll go to boosting. Classifiers are trained sequentially Each correcting errors from the previous one. Like we'll be training on, for example, decision trees, and then the and then the next regression one. Each will be learning from each will be learning differently. So finally, we can combine. For example, Adaboost, a popular posting algorithm that adjusts weights to focus on harder to classify examples. Weights will be adjusted so that it will be focusing on hard to classify examples. Advantages are robust overfitting and improves generalization accuracy. And the next one is pruning. After training, rather than using all classifiers, pruning selects a subset of the most relevant ones to improve accuracy and reduce computational cost methods. We'll go to order based pruning. Classifiers are ranked by their relevance using metrics like error distance or diversity. And the next one is optimization based pruning. Uses optimization algorithms to select the best subset of classifiers. Clustering based pruning. Classifiers are grouped into clusters and those closest to the cluster. Centroids are selected to maximize diversity and efficiency. Challenges are balancing diversity and accuracy is crucial. Pruning adds complexity but can significantly improve efficiency and generalization. Main approaches of transfer learning. Important sampling methods. We have, I think, around five methods. Important sampling methods, density ratio estimation, advanced domain adaptation, deep learning based approaches. Importance in important samplings will minimize the expected risk over a target domain. Like we'll be minimizing the risk for the target domain. We'll have we'll go through KMM, and which is kernel mean matching. It aligns the mean of source and target data in kernel space. Importance weighted twin Gaussian process learns importance weights via density estimation. Density ratio estimation. Estimate how likely a sample from a source is from source versus target. Techniques of density ratio estimation is CLEAP domain classifier. CLEAP uses KL divergence to estimate density ratio. Actually, KL divergence is from KL divergence we can find how much two are related. And the domain classifier trains a model to distinguish source and target data. And we'll go through advanced domain adaptation techniques. One is domain adversarial methods and statistical geometrical alignment. Domain adversarial methods, it reduces domain shift using adversarial training. It has some limitations it assumes that same label space across domains. It assumes same label space across domains. Which enhancement is unilateral alignment to address incomplete target label space, and statistical and geometrical alignment. It combines shared and domain specific features. It projects data to subspaces, maximizing target variance and the minimizing distributional shift. And next we'll go through dynamic domain adaptations, like which is deep learning based approaches. Weights distribution contributions dynamically. Examples are MDD and DDAN. MDD uses Grassmann manifold for domain adaptation. DDAN end-to-end deep network for dynamic alignment. Deep residual correction network. This is uses partial adaptation to match shared classes only. Reduces influence of irrelevant source classes. Let's see the main contributions. Novel adaptive architecture, it uses double graph Laplacian for adaptive dimensionality reduction. It combines local and the global, like mutual information analytics, which are two Laplacians. Adaptive future clustering tailors feature selection per sample to increase relevance and informativeness. Hybrid learning strategy applies ensemble learning and transdictive transfer learning on graph reduced data. Non-Euclidean matrix enables robust classification in complex non-linear high variability datasets, improved generalization and lower complexity for operational datasets. method. We'll go to the main method, how it is done. The architectural process is complex multimodal datasets using graph-based representation and spectral clustering for adaptive dimensionality reduction. The system represents the data samples as nodes in the graph, which selects the subsets of features per sample using graph clustering, preserving structure and redundancies. It leverages two Gaussians as discussed above. Uses eigenvalue decomposition as similar as spectral clustering, exactly spectral clustering. We have some challenges with spectral clustering. We have difficulty in identifying the number of clusters automatically, and also difficulty in identifying effective clustering with sparse data, and also difficulty in identifying similarity metrics capturing data variability. Top eigenvectors often fail in noisy and high dimensional multimodal. What's the solution? So we have some solution which was discussed in this paper, super sample based graph solution. Which means we'll partition data into super samples of similar characteristics. We'll be using two similarity matrices, Gaussian similar matrix. This is used for local feature similarity. This was the expression for that, and also mutual information based similarity used to evaluate global future redundancy, which is this is the mathematical formulation for this. This is slightly bit similar to KL divergence between two sets. And benefits of super sample clustering is local adaptation to preserve geometry or statistics, reduces redundancy while returning relevant non-overlapping features, sets handles heterogeneity in large multimodal datasets efficiently. And let's go deep into the paper, like mathematically. Join graph-based feature selection via dual Laplacians, adjacency and Laplacian matrices. These are the degree matrices, adjacency matrices. These are the normalized Laplacians. This is the kernel, and this is the mutual information one. And we'll see joint diagonalization for feature selection. Identify features such that the subgraph vertices are strongly connected by both similarity graphs. The optimization problem is formulated like this. And alternatively, we using joint diagonalization, which is Prompt's criterion. This is the Prompt's criterion, and these are the representations. And let's go to the results, which are most important part of our presentation. And we'll see the accuracy of ADR, which is adaptive dimensionality reduction, which is with respect to source domains. As source domain size increases, ADR increases, which includes better performance as the source domain size is increased. And let's for the ADR improvement percentage of with respect to source domain size. Its improvement decreases as source domain size increases because more source data provides sufficient information for learning, reducing the benefit gained from adaptive dimensionality reduction. ADR is most helpful when data is limited as it selects the most informative features to improve learning efficiently. Here, ADR improvement percentage increases up to some point with respect to number of weak class pairs and then decreases. And this is end of presentation.